Ah. All right, so now we have the second part of Wilhelm Schlag's talk on classical field theory.
Thank you so much. It's a great pleasure to be back here. I think I speak for all of us that this experience of our working group has been quite amazing. So thank you, Benoit, for agreeing to launch this experiment. We'll see how it continues. So I will not assume that you remember much from the first part, which was 6 weeks ago, but I won't be as, I will not go into as many details of the same material that I did in March. What PDEs are we talking about? We're talking about PDEs of this form. So X is on the line. And we're interested in the Cauchy problem with work, where W phi can be a number of different things. This potential energy then looks like this. It has potential wells at -1,1. That's called phi4. So this is the phi4 model, where there are still many open problems. Then there is sine Gordon. So what is sine Gordon? It's 1 minus cosine phi. And then you can look at minus phi 1/2 phi squared plus a fourth of phi4. And that's nonlinear sine Gordon cubic. And this is sine Gordon. And we noted that there is a conserved energy E of phi is 1/2 phi t squared plus phi x squared plus w phi dx. And we want this to be finite. That means in particular for phi4, 0 is not an allowed solution, which is kind of paradoxical. If you plug in 0, right, you would be trying to integrate the constant 1/4 over the line. So we want this to be finite. Special solutions are the so-called kinks. They connect these vacuum states. So the vacuum states would be W prime of phi 0, say equals 0. It's not good notation. I don't know. Vacuum equals 0. They are constants and of course satisfy therefore this equation. So for sine Gordon, let me write down the sine Gordon equation. 0 is such a thing, and then you can ask about stability of the 0 solution. So stability, whatever stability here means of vacuum. Now, of course, what intuitively it should mean is that if we start near 0, then we remain near 0. Let's see if this. So the natural question then, if given epsilon positive, does there exist delta positive such that if norm phi comma phi t, this is in phase space, h1 cos L2 is the natural norm. That's the energy number in delta, and this is at time 0, of course. Does it imply that, first of all, the solution is global? This is a supremum over all times, right? This is orbital stability of the vacuum solution. a finer question. So this would be one rendition, orbital stability of the vacuum problem. A finer question would be asymptotic stability. Would ask for a little bit more, or say, Schwartz data phi 0, phi 1. I admit that this is overkill. Yeah? You don't need Schwartz data. To avoid questions, how many derivatives do we need? What kind of weights do we need? The Schwartz data phi 0, phi 1. And epsilon small. So absolute epsilon much less than 1. I'm hiding here, you know, the question is, can you find an epsilon naught such that if epsilon is less or equal to epsilon naught? Then the evolution, then the Cauchy problem, say sine Gordon with data phi comma phi t at time 0 equals epsilon phi naught phi 1. So now we might want to say behaves for large times. Then we, of course, in this type of situation, we have small data. And as I said, hiding in here is also the question of global existence. So, final question, does the solution globally look like the free solution of a suitable problem? So what, let me be a bit vague. What does long-term dynamics look like? So in other words, what can we say about E of t to leading order? What is the leading order as time tends to infinity? If this is too vague, you can say, how does the L infinity norm decay as time tends to infinity? Then why might this be delicate? This is not delicate. Because we can use the energy as a Laplace function. Let's see how this works. So if we linearize sine phi, I can do it right here. So this is 0. Phi tt minus phi xx plus phi minus, how does it go? 1/6 phi cubed plus big O of phi to the 5, right? So you can use the energy coming from here is, of course, the H1 cross L2 energy, and you can treat this perturbatively because you have an L H1 to L infinity sublevels embedding on the line. And then you will see that since the energy is conserved, you can use it as a Laplace function. So absolutely yes. From energy, if you use it as a Laplace function. Agreed? Energy is conserved. Then these terms can be neglected if the H1 cross L2 norm is small to begin with, because you use that. For this term, you multiply by integrate by parts, multiply by phi, integrate by parts. So for integrate by 4, you find this, say, by forgive me for these trivialities, you have the integral of phi squared, and then you have the L infinity norm of phi squared. And the L infinity norm is on the line is controlled by H1, which you control. So much more interesting are the so-called, but before I go here to the topological solidons, what about this question?
So just the terminology point. So yeah, we have functional with something that
is a monotone quantity,
increasing, but also to be constant.
Yes. So the picture is your vector field doesn't have to cross, that your vector field can always be tangent to the level lines, and then it's still a Laplace function, but that Laplace function will not give you convergence to the equilibrium. It will give you no more than orbital stability. So why is this asymptotic stability question so much harder, and actually was only addressed around beginning 2000 by Delors? His paper is much more general, has much wider scope. He includes quasi-linear nonlinearities, but why is this delicate? Because of this term, because of phi cubed. If we were to try and use a comparison dynamics to answer the question, what should the leading order be at infinity, we might think of looking at this problem. Equals 1/6 phi cubed plus big O phi to the 5. And then you write down the Duhamel expansion. What people typically do is they introduce a new variable phi, say, which is 1/2 phi minus I phi t. But what is, you understand that this is the operator on the Fourier side is bracket C, have C. D is minus I del x, and bracket is √1 plus C squared. And so if you plug this in, you will see that your new equation looks like this. So what is phi? That would be v plus v bar cubed plus big O of v to the 5 and v bar to the 5. All right. And what is the dispersive? Why did we do this? Because we now have very conveniently just one initial condition. If you want to write it in terms of the initial conditions of phi, it's of course this. And notice that this will be H1, this is L2, so the whole data here are H1, or better, depending on what you assume on phi. And what is the dynamics of the free problem? So if you solve this, I'll use the same letter, maybe I shouldn't, and v at time 0, let's just call it v index 0. Then of course v of t will be e to the it acting on, I might need a minus sign. No, plus was correct. Acting on v0, which at x means integral 1/2 pi, and then very quickly e to the it bracket c, e to the ix c, v0 half of c c. Then let's look at stationary phase. You have x plus t c over bracket c equals 0. And you can work out where this happens. Let's just be patient and actually do it. X squared, 1 plus c squared equals t squared c squared. You just have to remember when we take roots to get the right sign. So the critical point x star, c star, sorry, x and t are given. So c star, wouldn't that be the same as x divided by root t squared minus x squared? Correct? You will recognize the Minkowski metric in the denominator. Okay? So is the sign correct? I guess not. Did I get the right signs, wrong signs? Here, then I need a minus, no? If x is positive, t has to be negative, t is positive. So when does this make sense? Only if absolute x less than t. That's not a surprise. We have to be in the light cone, all right? For this to make any sense, if we're outside of the light cone, a critical point does not exist, and then we can expect better behavior, all right? You know from stationary phase that the decay will be governed by the second derivative of this phase. This is I should give the phase a name. Phi is already reserved for my field. So then here, let's write this as e to the IT, and let's call this phase big psi of Tx psi, or something like that. And you see that big psi equals, what did I do here? So bracket psi plus x over t psi, right? And this is the equation up to a factor of t, psi partial psi equals 0 is equivalent to this. We computed it, and the estimate that we will now find so if we take a second derivative, then of course we get here we are second derivative. So then we have psi over Japanese psi prime derivative in psi, which happens to be psi minus 3. What is that? That's, here is a pair of lines. That is the curvature of the hyperbola. I'm going to put these. So here are the asymptotes. And what am I plotting here? So I'm plotting psi against Japanese psi, and here you have the other one. And of course, the curvature goes to 0 as you move up here into the asymptote. So that's psi minus 3. And what that means is that you have to pay 3 half derivatives, right? Because you get 1 over root t decay from your stationary phase, 1 over root of the large parameter, but you have to divide by the second derivative of the phase psi. So that means you have to, the root of the second derivative. So at the end of the day, what you find is this very standard estimate, line of right little f infinity in x, is bounded by constant. Now we say that we should pay 3 halves of a derivative. That's true, but then you have to do a little Paley partition and sum up. So you pay a little bit more in one, and nobody wants to drag that plus epsilon along. So we then just pay 2 derivatives. We take epsilon a half and we pay 2 derivatives and divide it by root 2. What am I doing here? Notice that this whole decay came from the fact that we have these, that's called the dispersion relation. That here, this is the graph of Japanese psi, this is the graph of minus Japanese psi, it's a psi axis. If we had the wave equation, which is 5, so forgive me for this trivial point, if we had the wave equation equals 0, then of course your solution is given by D'Alembert. Phi px would be the initial position x plus 3 plus phi 0 x minus 3 1/2 plus, you know, the integral, just for the sake of completeness of it, phi at 0 y and y. All right, so D'Alembert formula has no decay. So here, no decay. Where does the decay come from? For Dwight Gordon, it comes entirely from here, from this term. That's the mass term. Without it, this has no decay and we can do nothing. Right? But because the mass term gives us some stationary phase. These are the lines. So this is psi, this is minus psi. These are the dispersion relations of the wave equation. On the Fourier side, we have this characteristic variety, pair of lines, no curvature, no decay. But you see, why did I go through this exercise? Well, first of all, maybe it's instructive. Secondly, this looks really ugly. Let's replace it by t minus half. While this is good news, it's also bad news, because look at the phi cubed term. then what we expect, we might want to write absolute phi cubed of t and x. In the best of worlds, if we pretend that this is a potential, time-dependent potential times the field, we would write 1 over t, but we giving away a small parameter that doesn't really help, absolute phi of dx, right? So we're pretending that the decay of phi is governed by the linear decay, the free decay, t minus a half. We borrow a square, we get 1 over t. Epsilon comes from the small size of the data, and then we have 1 phi left. So then, if you have experience with scattering theory, and I know many of you do, yeah, that's bad news, because even though we have a nice Klein-Gordon on the left, sort of nice, on the right, we now have 1 over t phi, that is a long-range perturbation. So we cannot hope that the long-time asymptotics of phi is, or in this case v, which is equivalent to phi, right, is going to be governed by the free problem. In particular, if you know what a wave operator is, you cannot expect that the wave operator approximates the nonlinear evolution. It cannot. You will have a phase correction, and this is what this takes us back months when Patrick presented for cubic Hartree in 3D with no potential on the left. The whole machinery of long-range scattering in this case, you run into this because of the slow decay that you simply have. Now, so what is the theorem? Maybe to save time, I shouldn't really try and write down the precise theorem. It simply says that indeed for the vacuum state, so small, what was this? This is the Potok equation, Sine-Gordon Potok around the vacuum. Small data, the nonlinear solution exists for all time, and it decays like 1 over root t. It does decay like that. However, there will be, if you want to extract the leading order of the field, you have to pay something like e to the I, some constant that depends on the data, log t, and there's also a small factor, all right? I don't really want to go into these things. Benoit, you will talk a little about these phase corrections. Will you talk about phase corrections long range? Sorry. Okay.
Yes. Yes and no. So opportunity equation.
Okay. So the vacuum state is not what this whole working group is about, even though we can't understand the harder things without this. So we want to perturb around a big state, not around 0. And we call them kinks. And so kind of amazingly, I derived them via phase portraits and so on and so forth. What's our equation? Now we do not linearize the sign at all. Around 0, we leave it. And we note that there is a time-independent solution, which is magical. It's 4 arctan e to the x. Looks amazing. It connects 0 to 2 pi. So here is a horizontal 2 pi. So it will go exponentially to 0. It's symmetric, all right? Looks like this. And this is called the kink. Doesn't depend on time. It connects the 2 vacuum states. So here you have infinitely many vacuum states. Right, so 0, 2 pi, and so on and so forth. And they are stable. And so now we're connecting 2 of them, and we want to understand perturbations of these kinks. And we denote this, and this should be small, of course. And now everything is space and time dependent. And you can do the same for phi 4. So just for the sake of completeness, I'll put down phi 4. It's kind of a funny looking equation. Simply because this has the wrong sign. You see, this would be Japanese. If you do the symbol of this, it's psi squared minus 1, then you're trying to take a root. That's impossible. So it shows you that this, and what's really going on, you change from hyperbolic to elliptic when c is less than 1, but it's ridiculous. And what you're really trying to do is perturb around 0, which is not allowed because the 0 solution of this has infinite energy. Here's a zero is a non-solution of this. So what happens when this has a kink, and the kink is similarly magical. It's tanh of x divided by √2. It connects -1 to 1. Stick -1 in here, you'll see that you satisfy these. Yeah, well, these are the vacuum states of phi4. Coming back to here, when you linearize, you will obtain an equation in either case. Formally speaking, it's like this, HU, and then you have a quadratic term, you have a cubic term, and then you have higher order terms. Higher order terms. These coefficients alpha beta will typically not be constant. I'll write some down. So what happens here? H was SG sine Gordon is minus del squared plus 1 minus 2 sinh squared, sec squared x. And just for the sake of completeness, H by 4 is another Schrödinger operator. As far as I remember, it looks like this. It's also sec squared. They are part of what we called the Peschel-Tiller hierarchy last time, the Peschel-Tiller hierarchy up to these mass terms, which are, of course, as you now know from our discussion of the dispersion relation and the curvature that we need the dispersion relation to have. These mass terms here are all important. Without them, there is no hope of having stability. Now, so this, of course, opens up a can of worms. And again, what question are we trying to address here? What question are we trying to answer? It's the asymptotic stability question. I'm happy to recall the orbital stability of this story, which is very old. It goes back 40 years to the early 80s. There is a theorem by Henry Perez and Brzezinski that says that under very general assumptions on the potential energy, it's not just sine Gordon and phi4, but kink solutions connecting vacuum states are orbitally stable. Why? Well, because again, the energy comes up as a Lyapunov function. So the Henry Perez Brzezinski, sorry if I misspell this, around 82 or so, they said that if your field starts up close to a kink, so this is initial position, initial velocity, let me do it like this. So you give me epsilon, then there exists delta positive, so that if this is small in energy, then you want to say that for all times, you will be close to the kink. This cannot be true in energy. This cannot be true because if you perturb the kink, the Lorentz symmetry kicks in and will start moving. So you have note. And here, of course, I mean, you take the infimum over all possible translations. Note that with the kink, also the Lorentz transfer in kink into solution. This is now absolutely time and space dependent, of course. And gamma is the relativistic factor. Absolute B less than 1. They are also solutions. So if you perturb this kink by a little bit, then it will start moving, which is why you have to mod out the translation symmetry. And now on the level of the spectra, you see this because the spectrum of all of these translation invariant field equations will have a zero mode. The linearization must have a zero mode. And let's draw sine Gordon. Sine Gordon, the continuous spectrum starts at 1.
Just
yeah,
so
yeah.
The Lorentz is not a counterexample because gamma will be close to 1.
Yes, very good. So we discussed this a bit last time, but absolutely, thank you for reminding us. This in H1 will remain close to the Lorentz transform. It's a very important observation that you made. That because this is small, the V will be nearly 0, this will be near 1, and then the kink transformed via gamma will still be close to that. The crucial observation you made, it's enough to do the translation mode. And you see this already from the spectrum. And the spectrum is not generated by the Lorentz symmetries, but the zero mode is generated by the translation symmetry. So here is the continuous spectrum starting at 1. Here you have the translation mode. And what does that mean? Well, it means that H always, if you have a kink, then the linearized operator of K prime is 0. Because K prime is just what you get when you differentiate this in Y. And K prime for can you do this in your heads? What's the X derivative of this? Arctan e to the X. It's sech X up to a factor. It's 1 over cosh X. Okay. So here for St. Gordon, you have H of sech equals 0. Just for the sake of completeness, let's draw the spectrum for phi 4. It has a surprise that doesn't come from symmetries at all and makes phi 4 incredibly interesting and difficult. Phi 4 has resisted all attempts kind of at understanding asymptotic stability. Again, you have a translation mode, and this is for St. Gordon. For H phi 4, you now have to take an X derivative of this. So what you get is sech squared of X over root 2 is the 0 mode. And so both sech and sech squared are positive. So these have to be the ground states immediately, just by oscillation theory. The ground state is positive. These eigenvectors, eigenfunctions must be unique, must be simple. So there is no negative spectrum. Can you read this? H phi 4, this SG, St. Gordon, HSG sech. H phi 4 sech squared X over root 2 equals 0. Sorry about the scribbles. Because of this root 2, you have it there too. Here you have something amazing. You have a discrete mode here, and it is H phi 4, if I remember correctly, sech tanh equals 0 up to a root 2 factor. Okay. And then both of these models have something kind of annoying. And you can ask, why does this happen? No idea. It is very specific. If you perturb these potentials a little bit, you will destroy what I'm about to say. There's a highly non-generic behavior of these linearized operators. You have what's called a threshold resonance. In fact, both of them have a threshold resonance, which is explicit. I think here the threshold resonance function is tanh. So maybe you can try to do this in your head. So if you do minus del squared, where is the linearized operator here? Minus 2 sech squared X, and you apply this to tanh X, you get 0. And since this is shifted by 1, if you do plus 1, you will get, so put plus 1, you get tanh. And this is called a threshold resonance because tanh behaves like an eigenfunction of this guy with eigenvalue 1. So it's at the edge of the spectrum, but it's not L2. So it's a L infinity, but not L2. And that is exactly the definition of what a resonance is all about. Now, why do these operators have this magical behavior? It's because they are part of the Purcell-Taylor hierarchy, which is a mysterious thing. If anybody can elucidate these things for me, I'd be grateful. L plus 1, sech squared X. And L here, to avoid triviality, so what am I doing? L greater equals 1. H0 is just a free word. So this has a name, we'll find it.
I'm listening.
This is
It's silly. I'm sorry about the noise, but it's the fire alarm in the building across the street.
Oh, I didn't. I am so enraptured by this man that I didn't. Special teller hierarchy. And this special teller hierarchy has absolutely magical properties, but before any of you interrupts me and says, well, your 5-4 linearized operator is not part of the special teller hierarchy, careful. So this is exactly, what is this? This, in this notation over there is H1 plus 1, agreed? H1 plus 1. Now you will say, what on earth is this? So you have to change variables. If you call this variable, I don't know why, for lack of a better letter, you read, you undo this, you will find that this becomes a 6, and then that's H2. So H2 is what comes up, and if you had started with a slightly different nonlinearity, you wouldn't get, of course, these operators. So they're highly non-generic. And what is the effect of these threshold resonances? They are mysterious creatures, if you want to call them that. And let's talk about them a little bit. But I should say, are there any questions? Interrupt me at any moment. Anything unclear? So what's the effect of a threshold resonance on the dispersive decay? Yes, please.
Just out of curiosity, where they come in the first time?
Say it again.
What is Schlag and Teller?
Oh, this is ancient. Their paper is from 32 or something like that.
But what was it about?
Good question. What quantum mechanics?
Does it come with some kind of spherical projection of a certain operator?
I didn't look at the original paper. But it's very, very clever what they did. They didn't have computers made for Mathematica, right? So they realized that with a tanh substitution, you can convert this into hypergeometric ODE, very special hypergeometric ODE. In fact, if you know what this is, they are all reflectionless. So R as a function of C, the energy variable, is 0. The reflection is identically 0 for all of these. But
yes.
the nonlinear analysis, I don't know how directly or not this is affected.
One
All
can't
right.
know everything,
Yeah.
can one?
Somebody's talking.
Siri is so long.
Siri,
That's
what
a
is-
question.
maybe Chat GPT is talking to us. All right. So let's talk a bit more abstractly. So let's, in more general terms, minus del squared plus V. And V is a nice enough, let's be slightly ridiculous and say it's a Schwartz function. Well, all our examples are of this type because sec squared is a Schwartz function, yeah? And we don't worry so much about optimal assumptions on V here, and of course it's real value. And then we want to study the scattering problem. To all of you who have now been working with distorted Fourier transform, this will be very familiar, albeit we're now on the line. And you see, in contrast to the half line, where the eigenfunctions or generalized eigenfunctions have multiplicity 1, right? In your problem, multiplicity 1. On the whole line, you have multiplicity 2. So the objects we introduced back in October, the Weil M function, they're actually 2 by 2 matrices, right? And this might sound strange because then you say, well, the distorted Fourier transform for the V equals 0 is your favorite object, it's e to the I, V equals 0, right? Are we being ridiculous? This is the Fourier basis. But you do it over the reals. So then you have a vector cosine sine. And if you look at Gestesi-Zinchenko, for example, they developed the formalism of the Weil-Titchmarsh function via 2 by 2 matrices. The M functions are 2 by 2 Herglotz matrices. All right. So they're positive definite for arguments in the upper half. All right. Now that was a little bit of a tangent. What are we after? We're after studying the scattering problem. And forgive me if all of this is completely trivial for you, you're familiar with all of it. And we demand that f plus minus x psi is asymptotic to what I just had here before. I should have left it. So e to the I x psi as x tends to plus minus infinity, and then I should stick a minus here also. Right? And then you convince yourselves by the Volterra integral equations, which you saw, right? You do the perturbation problem around these. And then you will find that, so the theorem is, here is a lemma. There exist f plus minus solutions of this, and of course, psi here is any real number. You can put them in the upper half plane, you just have to be careful, right? You want exponentially decaying them. So the theorem is that there exist these solutions of these equations and they have this asymptotic behavior. And then the picture that's typically drawn is if you have a potential, let this be your V. And it's particularly nice if V actually has compact support because you're dealing with ODEs, then these f plus minus are actually identical to these guys outside of the support of V, right? By existence uniqueness of ODEs. And more generally, so the picture that's really quite nice, but could be misleading also, is that you send in a wave. So you think of sending in e to the ix psi, then part of it is transmitted as transmission coefficient e to the ix psi, and part of it is reflected, then you get a reflection coefficient e to the minus ix psi. And then people put an r minus here. So what does this suggestive picture actually mean in terms of equations? Well, something quite obvious. So you have to replace this plane wave by these Yost solutions. They are called Yost solutions. So the exact rendition of this scattering picture is that you have t psi f plus x psi. That's the transmitted wave, is the incoming wave, which is EIX psi. That is F minus of X minus psi. So you write F minus of X minus psi. And then you write the reflection coefficient R minus of psi of F minus X psi. And you have the analogous picture if you just flip X with minus X, all right? And then you have the fact that the so-called scattering matrix, I believe this is called S psi, it's T psi, R plus psi, R minus psi, T psi. This is unitary. So absolute T squared plus absolute R plus minus psi squared is always 1. And as you can imagine, the Wronskian of F plus and F minus will play a special role. And that happens to be, if I remember correctly, transmission coefficient psi times the Wronskian is minus 2x psi. This is a highly significant equation. Why? Because it shows you that the Wronskian between F plus and F minus cannot vanish. So this is not going to be 0 if psi is different from 0. Okay? Now look at the free case. Look at V equals 0. So V equals 0 is non-generic. And I'm using this term on purpose. It's not some vague term that I pull out of thin air. The research literature, in particular in classical field theory, look at the paper by Germain Busateri that I should really get to, but you know, there's only so much time, is non-generic. What does this mean? Well, what are the Yost solutions for the free case? They're e to the I x psi plus minus, precisely, right? So what are transmission and reflection coefficients? You put 1 here, then this is identical to that 0. So then the transmission coefficient is identically 1. and the reflection coefficient is identically 0. And the Wronskian of f plus, f minus, at psi, which is of course x independent. What is it? Isn't it minus 2xi, identically? And what are the zero solutions? The zero solutions, f plus x 0 plus minus, are just constant equal 1. Good? So you get a constant function. This is the quintessential example of a resonance function. Notice that here, the threshold resonance, what did we say? It was given by Tench for the first special teller. So you have H1 of -2. So H1, check it, maybe check it with mathematics, and you can embarrass me terribly by checking in real time that this is false. Or check it in your heads, H1 Tench is 0. Okay? Did I do something wrong?
No, it's correct.
Correct, good. Correct, okay. I can be right sometimes, occasionally. So H1 Tench 0 is another example where you have a bounded solution at the threshold, but not L2. And why? So this is called, so 0 is a threshold resonance. So let's discuss this concept a bit more systematically. Why is it called a resonance? Remember that I insist a resonance. I never use the term resonance casually. A resonance is a small divisor. Where is it hiding? Where is it hiding? You see it if you do the Laurent expansion of the resolvent as you approach the origin, but you have to approach it, from the right direction. So minus del squared minus z squared minus 1xy, and take mz positive. This is the free resolvent that's exactly v equals 0. What does this resolvent kernel look like? It's e to the iz absolute x minus y divided by minus 2iz. All right? Notice, let's do something trivial. It is 1 plus iz x minus y plus minus 2iz. So that is 1 over minus 2iz minus 1/2 x minus y plus other stuff. Your small divisor, so here's, forgive me for this trivial picture, here is the upper half plane, this is where z sits. Here is 0. And now we want to Laurent expand as z approaches the origin. And you see that you start your Laurent expansion not with a 1 over z squared. You cannot. 1 over z squared would only be possible if 0 were an eigenvalue. I will convince you very easily that it can never be if v is reasonably behaved at infinity, just like here. This is the expression of a zero energy resonance. Here is your small divisor. What is this? Do you recognize this? Forgive me for this trivial question. What is minus 1/2 x minus y? The fundamental solution of minus del squared. So minus del squared of minus 1/2 x minus y is delta of x minus y. It's the Green's function of the free Laplacian. Okay? Now contrast this to, this was just the Laplacian in 1D, just for laughs if you want to. Do the same thing. What's the Green's kernel in 3D? R3. It is e to the iz x minus y, must be exponentially decaying, over 4 pi, you've seen this many times, x minus y. No small divisor as z tends to 0, so the function constant equal 1, which of course is a solution to the free problem R3, is not a resonance function. Why? Well, that's a good question. The short answer is because of the decay of the Newton potential in R3, a resonance function has to decay like 1 over r in 3 dimensions. So April knows this story extremely well. And 1 over r is not L2 in 3D, of course. Yeah. So people get confused about what resonances mean or not mean, including me, okay? Because we could be here for a long time if we try to systematically cover in every different dimension what they mean. By the way, in dimension 5 or higher, they never appear. Because in dimension 5, how does it work? This is 1 over r cubed to leading order. Yeah, but that's L2 in 5. You see, so starting dimension 5, if the potential decays reasonably, 0 is never a resonance, please.
And just for completeness, how is this different from other in the quantum spectrum? Like, what would you have if you try to put it not at 0, but at 1?
Well, then you have no small divisor, which is an expression of what? It's an expression of the fact that the Wronskian doesn't vanish for non-zero energies. And remember that the Green's function has the Wronskian in the denominator. Okay. Now, okay, so let me convince you with another picture that a resonance can never, so at the threshold, you can never have an eigenvalue. This is no accident that you start off with 1 over z and not 1 over z squared. You cannot possibly have an eigenvalue. If you did, then of course, if this operator had put any operator here, h, and if h phi is 0, isn't it true that h minus z squared inverse phi equals minus 1 over z squared phi, no? Right? That's true. Insofar as the inverse exists. But be careful. So for this to make sense, phi would have to be L2, because that's an L2 bounded operator if z squared is a resolvent of h. So that only makes sense if phi is in the Hilbert space L2. And then you would start off with 1 over z squared. Why do we not start off with 1 over z squared? Well, because what we're really doing is, let me redraw our potential, whatever it may be. And on purpose, I drew it of compact support. So trivial question. What's the fundamental solution here? Of what? Of minus f double prime. So solve this equation, please. 0. C is 0. Okay? And V has compact support. To the right of the support, what's the fundamental solution? It's the fundamental solution of minus f double prime equals 0, fundamental system. So the fundamental system is 1 in x. Yeah, here also 1 in x. So then what is a resonance? Resonance means I send in 1, and then something weird happens, and then I connect to a constant. I do not connect generically. I will not connect to the constant. I will connect to x. Constant times x. Are you with me? Connection problem. You send in a constant and you ask, does a constant come out, or do you pick up this? And resonance means you do not pick up this. The free case, you send in 1, you stay 1 all the time. Partial teller, you send in 1, you do something weird, and then can you imagine you come in with a tanh and you come out with a tanh. Magic, okay? Or for phi 4, you would send in 1 minus 3 half sec squared, and then you come out with 1 minus, you see? You send in 1, asymptotically you come out with 1.
Is there any potential that you can cancel this resonance in one dimension, or
What do you mean cancel?
like any potential when you perturb your one dimensional?
Very good question. So generic, what happens? So non-generic, remember? So what's the opposite? Opposite generic means that you end up with this. So generically, which is a term I don't like to use casually, generically, the Wronskian between f plus 0, f minus 0 is not 0. I mean, what am I doing here? generically, this this is not zero, of course. The non-vanishing is generic. And if you remember the formula, the transmission coefficient T of xi is minus 2xi divided by the Wronskian. Let me just say plus minus so that I always have to write this. This is W plus minus psi. Is this. So the Wronskian, this shows you something. The transmission coefficient is always less than or equal than 1. Why? Because absolute T squared plus absolute R squared is 1. So this is always bounded by 1. So this cannot blow up as xi tends to 0. So this means that if it vanishes, which is the non-generic behavior, that's the definition of non-generic in this context, this can only go to 0 linearly, only linearly. And if you, so Ebro, if you take a potential and you perturb it by epsilon times a Schwartz function, then it follows right from here that for almost every epsilon, it will be not 0. And so now you see from this picture, you cannot generate L2, because how can you build L2 from 1 and x? The only thing, the best you could hope for is constant. And this, if you've ever heard this term, there is something called Gilbert-Pearson subordinacy theory, all right? Very nice thing. Can't go into it, but what's a subordinate solution? The subordinate solution is unique. You see, this is the bounded solution is unique up to a linear multiple, up to a scalar multiple. X is unbounded, but it's not unique because any coefficient Cx plus C twiddle, this is bounded if and only if that's 0. That is why 1 is called the subordinate solution, because it is unique up to a scalar multiple. Adding on X, you have infinitely many possibilities. So what's a resonance? There exists a globally non-zero, obviously subordinate solution. Globally subordinate solution. Now, I have to wrap up soon. What are the dynamical consequences of this small divisor? So any questions? Have I convinced you of what is a zero resonance? It means, so I could write down a TFAE theorem. The following are equivalent. You know, the Wronskian vanishes between F plus F minus at 0. That's equivalent. Now, this is funny that the transmission coefficient at 0 is not 0. The vanishing of the Wronskian at 0, which is non-generic, is equivalent to the non-vanishing of T at 0. That's perplexing because non-vanishing should be generic, but it's actually non-generic of the transmission coefficient. Then that's equivalent to the Laurent expansion of the resolvent, albeit now with a V, starting off with some coefficient divided by Z, and coefficient, that's a rank 1 operator. It's the projection. So let me be a bit less mysterious. Any questions about the 3 decays? Ebro can explain the 2 decays much better than I can. What are resonances? 2D is fascinating because they're the so-called S wave resonances and the P wave resonances. Ask him. No, you have written papers on this. So H is minus del squared plus V, it's there. H minus Z squared inverse. We'll then start off with the projection E tensor P over Z. Maybe there is a coefficient, and then plus big O of 1 has, first of all, you need in Z positive, and you need Z to tend to 0. In what crazy sense do I mean big O1, bounded? Well, look at this. When, in what sense is this kernel bounded? Well, as a bounded operator in weighted L2. So you always interpret this as in operator norm, in op norm, in some weighted L2, and you can be very generous with the weights. This is universal in all dimensions. You just put weights and you do these Laurent expansions. What's the consequence of this small device? And what's phi? How could I not say what phi is? well, h phi is 0, and we're in one dimension here. Okay, so then this phi has to be unique. And this is not an L2 bound, this rank 1, you know what it means. So phi tensor phi acting on F is integral F phi, that's a number, times phi. That's a rank 1 operator, albeit, look at it here. What is phi? It's 1. So this actually is a kernel 1 tensor 1, but nobody writes 1 tensor 1. What is the effect of it? What is 1 tensor 1 acting on F? It is the integral of F of x dx. Nobody writes 1, 1. But that's what it is. All right? It's the coefficient of the constant function 1. And so let me kind of stop here. What is the consequence of this in the nonlinear theory? Well, so let H be like over there, like it was here. And now let's look at the, you know that we have to use Klein or this is, right? This replaces Japanese, what did we have there? We had Japanese Xi. So this is root Xi squared plus 1, albeit now in the distorted energy, Xi squared, right? Relative to the S. And now let's allow for discrete spectrum. So I put here the projection of the continuous spectrum. And now I want to understand what happens if 0 is indeed a threshold resonance. Then you pick up a constant, you have e to the I pi over 4, this is a positive constant. You pick up the root t decay, that shouldn't surprise you, we had it from stationary phase. Then you have e to the it, which comes from this 1, because the threshold resonance happens at energy 0. Stick 0 here, you get e to the it, that's exactly that. Those things come from stationary phase, I'll just eliminate this. And then you have phi tensor phi, exactly the resonance function. So this is an L infinity function. Now, we are applying this to some function f. And then we will localize. So put the x minus 5. And then put L2 on the line. And this is bounded by a constant t to the 3/2 norm x to the 5f in L2 on the line. And this holds for all t greater equal 1, and it holds for all Schwarz functions f, but of course you can then pass to limits. And so this is well defined. This means phi times the integral phi f. And what's the significance of this? Do I have 5 minutes or no minutes or what? 5?
Yes.
So notice that if you don't have a resonance at 0, then this doesn't show up at all. Then phi is 0, right? You only have the trivial solution of which phi is 0. So this is the case when phi is not 0, but you can say, well, it includes phi equals 0, fine. Then this doesn't appear at all. And what it says is that we seem to have beaten stationary phase, which is very strange. Before we had, what did we have? By the way, for the same operator, irrespective of whether it's generic or non-generic, you now know what this means. It means 0 is non-generic, means 0 is a threshold resonance, generic, not so. Irrespective of the type, generic, non-generic, you will have this estimate in complete analogy to what we had before. And here you put, well, you can, so careful, t minus a half. And then I put here 2 derivatives, 3/2 plus epsilon, just put 2, L1 on the line. See this L1, L infinity decay that came from stationary phase does not care whether you have a 0 threshold or not and the resonance. Now, this is amazing because if this isn't here at all, so if you're generic, then it says local L2, you seem to beat stationary phase. Because this is local. You see, the logic here is that if you have data supported near zero and you're an observer sitting near zero, which is the effect of that, then you will see only tails that decay faster than 1/√t. And that's very good news because this is integrable at infinity. So the way you should imagine your wave is that the crest of the wave decays like 1/√t. It will also disperse so that you have L2 conservation or energy conservation. And here you will only see tails that are of the form t minus 3/2. Does this make sense? So this you can never beat. That's that. But just like in your, right, the Adam, Abreu, and Jiahua, and Bruno, you're trying to get t minus 3/2 if you conjugate by r prime. Yeah, that's because, this grows like t. This distance should grow like t. So, and if you ride this crest of the wave, you can't do better than that. Here, it shows you that the resonance is devious. The resonance will mean that you decay near the origin on the level of this phi, no better than the crest of the wave. Albeit this phi, well, it can be the constant one. So that you will say, what's going on here? Because phi equals 0. Yes, you can put here minus del squared, no potential. Then this is 1 tensor 1. So it shows you that this 1/√t decay, at least in the local sense, will come only from the resonance. Otherwise, you have t to the minus 3/2. And on the nonlinear level, this makes a huge difference. Let me show you. Because this resonance, which is now precisely defined via Wronskians and these solutions, allows you to, yeah, please.
This is it the first simple expansion?
We haven't tried this, so this is in the paper L squared S squared. This is Lindblad, Luhrmann, myself, and Sofa. This from 20. And how did we get this? Well, you can't use the distorted Fourier transform, it seems, to get this. We use the Stone formula that you know well. The Stone formula appeared in October. You write the resolvent as a Green's kernel, and then the Green's kernel doesn't have tensor structure. So you have to distinguish x less than y, x bigger than y. That's not tensor, right? Tensor means function of x times function of y. The amazing thing is that at energy 0, the resolvent does have a tensor structure. This is, in Texas, they're trying to abolish tenure. So we're bringing it back with tensorial structure. Yeah, so at 0 energy, the resolvent has a tensor structure. That's the next term we never tried to control. How do you prove it? You pull out this from the resolvent, and then you directly appeal to a theorem in Hermander volume 1. You can literally pull off the shelf. It's beautiful. This Hermander was so accurate about the error terms in stationary phase. So this you can get by computing, bounding the error term in stationary phase. That's stationary phase, but on the 0 energy term. Okay.
So whatever you have to say, it can have finite rank. I don't think that.
That's a very important comment. That's a much more intelligent comment than I made. So the essence here is that this is rank 1. So Abreu, you think that the higher terms do not have finite rank, and I would agree. I would agree that Abreu is absolutely correct, that the next terms are not finite rank. I believe this makes perfect sense. They don't come from projecting onto a few enemies. Very important. Compact in which sense? This guy is not even bounded in L2, so it doesn't make sense as compact. It's L infinity tensor L infinity, so it's not an L2 bounded. So yeah, so you in weighted L2, this is compact, of course. So I would say there is no reason that the higher correction should be compact. No, right? Or what is your feeling?
Yeah. For sure, it maps weighted out with the weighted out, with that part out. But I don't think.
And so the fact that the stationary phase, you have a complete extension. There is no analogy.
We've never gone beyond this term. And I'm now starting to wonder whether There is a deeper reason. We didn't need to, because this is already integrable in time, you see. We gain nothing from that. This is integrable at time infinity. So for the perturbation problems, it's enough. But in local norms. So if you have patience, I can tell you a little bit about how this affects the quadratic term, or we stop here. And it's entirely up to you.
I think since we've gone all this way.
You want to see me crash and burn, okay?
Keep the pain.
Since you use the word pain, I cannot resist this, but am I on, I'm being recorded? So I know that some of you have come through. So speaking of pain, to me, the word Princeton is linked to the word pain. So Kavi, you and I spent some time there. And I was a young assistant professor there and had to teach 2-2. Yes, to you young people, yeah, we taught 2-2. And I was, the tradition at Princeton was the grad students were always asking for introductory grad courses. And the chairman, like, you know, Stein and Joseph Cohn, they said, no, 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 this is Princeton, you learn everything by yourself. You just take the qualifying exam and good luck. But Charlie Pfefferman as chair listened. And then, you know, a bunch of us were told, so you teach an introductory graduate course. The catch was that I also had to, you know, be the lead instructor for linear algebra and multivariable calculus with 6 teaching, you know, with 6 instructors and 300 students and this and that. So I went to the chairman, Charlie Pfefferman, and he listened, and then he said, let me give you a Bill Clinton answer. I can feel your pain. And there I was, I got to teach, you know, my linear algebra, multivariable calculus, and my graduate course in harmonic analysis. So let's have some pain. Suppose we have this like before. We have this linear problem, and now we have a coefficient. And let's ignore what comes here. It's fine. There are papers in the literature just like L squared, S squared, also Germain-Pusateri, that stop here. However, Germain-Pusateri does something very difficult. They consider alpha like this, so they're allowed to, you asymptote to a constant, you asymptote to a different constant.
Can I say something about this operator?
I'll have a seat.
Sorry. But I think that operator cannot be compact because it cannot give differentiability to a function f.
Which operator?
So whatever operator you have over there is indicated.
You mean at higher order?
Yeah.
Okay.
So you cannot give the f differentiability, so it cannot be compact.
It sounds very reasonable. Okay.
Sorry.
So I will not deal with this because that's hard, okay? And their paper you can look at, it's like 180 pages long. So let's take alpha to be a Schwartz function, and that's not unreasonable because for sine Gordon this happens to be sech tanh. Yeah, well that's a Schwartz function. Yeah? And so now we will make the following ansatz. We will just, first of all, we replace u as before by v, and v is 1/2 u minus, what was it, I, the inverse ut. That's L2 if u is, so what is this? This is H1, if u H1, u L2. And then we have to solve the equation Vt. It's a first order now, but we have a complexified field minus I del V, and that's, sometimes I forget this factor. This is terrible. Alpha u squared. What's u? It's v plus v bar over 2. No, actually it's just v plus v bar squared. And we will here. Right? Now I'm doing this on the free case, but I could also do it on the level of this thing here. So then instead of bracket D, I would have to write what? I would have to write root h plus 1. Are you with me? Right? Root h plus 1 and h, just to repeat the inevitable. So this is minus p squared plus v, but you know this cannot work if v is a fourth function. I have to add a mass term. So let's add 1. Otherwise, I have no decay whatsoever. This is the plus 1 here. So no, let me do it like this, h plus 1 to be consistent with my notation. So then we are indeed in this context, we have h plus 1, and the free case is included again and again, and this is just 1, you know, 1 tensor 1. And so then we would write v at time t would be e to the I t, is it plus or minus? It is plus. T, or you replace it by root h plus 1, and then you should project onto the continuous spectrum. Data, and then we have the Duhamel term, 0 to t. We have 2iv inverse. We have e to the it minus s v, or root h plus 1 with a projection pc. And then we have this stuff. We have alpha, v plus v bar, but now at s, alpha is time independent squared ds. And now we want to understand the so-called profile. So the profile f of t would be e to the minus itv v of t. Those of you working with wave operators, you will immediately recognize this, right? This is the perturbed evolution, but pulled back with the free evolution. So this is like, yeah, the limit of this should be the wave operator data, whatever you want to call it, plus 2iv inverse. So this t goes away, then I have 0t, e to the minus isd. And now we will be bold and stick in the leading order coming from here. Why are we allowed to do this? This is local. Yeah, but I said that alpha is local. Alpha, such times, something like that. So since alpha is local, I am the observer sitting near the origin. I am that observer. So what I will do is I will plug in the rank 1 leading 1 over root s decay, correct? So I write alpha, and schematically, you have a bunch of terms plus minus because you have to allow for all combinations. That's very important, of course. But I will pick up, for example, e to the 2is. That's what I get when I square this. I will ignore that constant, but certainly not that. Or if I want to stick an I here, e to the 2 pi I, then I have divided by s, and then I will have what? I will have phi squared. Notice that I'm kind of hiding this number, phi f, that's the integral phi f. I don't expect anything dramatic from that. So to leading order, this is what I have to pay attention to. Are you with me? What am I sweeping under the rug? For example, v bar would give me minus 2s, but you see that that's a great term because I have no cancellation in the phases. For the experts, there's a time resonance. All right, so on the Fourier side, meaning on the Xi side, and that makes perfect sense even if h has a potential, right? Because what is c? C is this variable, c squared f plus. So it's the energy relative to the distorted Fourier transform which you get from the scattering data from f plus f minus. So on the Fourier side, we will have an integral t, we will have e to the, let's pull it all together, 2i, no, I. Here we have 2s, s I pull out, is, sorry, I'm getting tired, 2 minus bracket c, Japanese c. That works with a potential, without potential, it's all the same. And since I pass to the Fourier transform, I have to write alpha v squared hat of c ds over s. Are we in agreement here? And notice what happens exactly at psi equals 2, bracket psi equals 2, that means 1 plus psi squared equals 4. and that is psi equals plus minus root 3. You might remember from March, I had these crazy numbers, plus minus root 3, these special resonant xi. Where's the resonance? Where's the small divisor? Yeah, of course, you integrate by parts in S. What is so unpleasant here is that this gives you logarithmic divergence at xi equals 2. Xi equals plus minus root 3. Bracket xi equals 2. When this vanishes, you grow like log t, unless, of course, so this will be log t alpha phi squared, what am I doing? Alpha phi squared hat with plus minus root 3. All right, and that log, of course, is somewhat surprising because it will destroy the 1 over root t decay that you have in the free case. So this quadratic term, because of what? Because of the threshold resonance of the linear guy. You see how this works? That the threshold resonance of H generates possibly a quadratic resonance in the nonlinearity, but only the resonance. And in L squared S squared, we followed up on such a discovery by Lindblad, Lehmann, Soffer just in 2019, where they considered V equals 0. They had the free Fourier transform, and they didn't really connect the notion of a resonance to this log divergence. But now you see with your naked eyes that this log divergence comes from the threshold resonance, but albeit non-linearly. And of course, this does not happen if this vanishes. And guess what? For sine Gordon, it does vanish. And this you can then call a null form if you want to, or whatever you want to call it. We call it a non-resonant condition or something like that. Only because of the vanishing of this at plus minus root 3, do we avoid this? We can integrate by parts. Our small divisor doesn't harm us because here we have alpha squared hat of psi. Yeah, this is bounded because it vanishes. Okay. And then you have the cubic nonlinear term that you have to worry about. But because of in sine Gordon, our perturbative asymptotic stability work, we can do normal forms of the quadratic term. We're left with the cubic and then the machinery that Patrick sketched, and maybe you will talk about it, but you spoke about it in the past also. This then controls the cubic nonlinearity, this profile, stationary phase, ODE for the profile, and so on and so on. Okay, thank you.
Any questions?
So Adam and Benoit, yeah, Adam. That's an extremely important question, and I don't know if I have the authorization from Lehmann to talk about that, but he had a student, and I think you met Yomni. You were a second player in the total, so he has a PhD student, Yomni, who actually is now verifying successfully that the same magic vanishing happens, to your point, for cubic NLS. But it's much more complicated because for cubic NLS, you don't have scalar distorted Fourier transform, it's vectorial, right? So you have to say it again.
2 by 2.
2 by 2. Okay, so this scattering theory goes back to the very nice work of Buslive-Pellman from 92, and then Krieger and I added somewhat to it, but it's really Buslive-Pellman's formalism completely. And within that formalism, he discovered, and I saw the formulas last week. I was at Texas A&M. They are long, okay? And he told me that I think Mathematica needed hours to compute the Fourier transform of some creature which has sec squared, tan squared, God knows what in it. And then you have and then you see, we also did this. First, you can do a residue calculation. This really means distorted Fourier transform relative to Herschel-Teller operator number 1. You can do this by residues. Then we did the Dabou transform. We reduced everything to the free Fourier transform. You get some alpha squared times cubed. This is 1. So you Fourier transform it, you get a factor, xi squared minus 3 times a whole bunch of other terms. How magical is that? Okay, and so, Adam, this is a very important question here at ISOM, actually, we know that ISOM is here in Providence. Capella in the December 21 made such a comment. He said he believes that it's not, Benoit, you had this complaint that it's not equivalent. No, no, no. So complete integrability generates this vanishing, but not the other way. But we don't understand this at all. There is no abstract theorem in infinite dimensions that would say that if you have lax pairs, then I don't know. At the moment, we're at a very primitive stage where we have to check this case by case. And Texas A&M, so this PhD student was checking it successfully for cubic NOS. There is magic vanishing, okay? And I can also say that Lührmann and Gongchen, we are working on moving kings, and there you need more than this vanishing. So with Gordon moving, it looks like you need several vanishing. Okay? The goal is to develop a perturbative theory that doesn't rely on complete integrability. But you're discovering that at least for St. Gordon, you need these vanishing miracles. And for 5.4, I mentioned that this is so important in 5.4. This cannot vanish. Because if it did, the internal mode, which is linearly, doesn't decay, it's linearly unstable, if you want to call it that. That's the wrong word. It's orbitally stable, but non-decaying. It's not asymptotically stable, the internal mode. The non-vanishing of this is responsible for the coupling to the continuous spectrum. Last time I couldn't think of the title of the very beautiful Sofer-Weinstein paper. It's radiation damping. This phenomenon is called radiation damping, that the internal mode non-linearly is coupled to the continuous spectrum, and then by some magic with normal forms, you show that a Riccati equation has a decaying solution, which is the coefficient of the internal mode. So Lührmann and I have understood such things for, and we are sure not the only ones, you're not vegetarian, but we can't close the whole thing. So for 5.4, this doesn't vanish, and then there are these monster expressions, and you see that you can generate the Riccati, but we can't close the, can't bootstrap the whole damn thing. It's okay. Sorry.
Is there a way to characterize this thing, let's say, without the distorted movement, in the sense that if, so this is the meta theorem, if so and so, which has to be clear, then this cancellation comes.
So can you say your hypothesis? If what happens, then
Well, if the structure of the equation is something
we have no theorem of this kind. None.
sort of like distill this cancellation into like a more general thing out of other than checking.
We
Maybe you could say a sufficient solution.
nothing exists like this. We don't know. Where is it? Maybe I'm just blind. And it cannot
Because it
be.
feels like super generic. Right? So far, almost, let's say, half of the cases that it tries to work after a lot of effort.
Well, in nonlinear Klein-Gordon, the nonlinear cubic Klein-Gordon, no, what did we look at? Yeah, nonlinear cubic Klein-Gordon doesn't have, because it's not completely. Sure. So it doesn't happen, and that's why we can only go to exponentially large time. Yeah. We cannot use normal form. We have to use this dyadic norm that measures how close you are to this frequency, similar to cannot disappear.
So it still feels like super generic. Or
Super generic.
to some extent, I mean,
The vanishing or the non-vanishing?
the vanishing. Or
Vanishing is highly non-generic. We know of it in two cases. One is Klein-Gordon, and the other one is this. I shouldn't announce it, but it's stable enough. It's cubic anyway. So, but 5.4 cannot have it. Precisely for asymptotic stability cannot have it.
But isn't there some solution to the formula? So you're looking at the corrective term.
Yeah. Two other terms, the V bar squared, V bar.
Yeah, so in the thing that you wrote just below, there should be the integral of f times p.
Yeah, so this I ignored
And
because
this is the only thing, so if this guy were to oscillate.
if this does something good, it helps you, but it doesn't help you.
not?
If we didn't get anything out of it.
But if you just multiply this equation by 3, then you should be able to get vector solution for it.
Well, the logic for, well, we have to discuss this, look at the details, but I'm telling you that this is what our analysis showed. This L squared S squared thing. We showed that if this doesn't vanish, then this log T slowdown actually does occur.
Yeah,
It does
maybe along the energy that you can control.
No, the theorem, no,
That's
look,
secondary dynamic in log T.
I understand that you might have a log T in the phase, and that's actually very, very important if if we try to go to infinity. But here is the theorem, and that's really a theorem in L squared S squared, that you can identify conditions. It's not enough to just have alpha phi squared non-zero. You also need some coefficients to be non-zero there. You can extract the leading order behavior, and you will see that the wave decouples into, at these frequencies only, it decouples into a wave that decays like log T over root T plus something that decays like 1 over root T. So it does do something bad. It's not just an upper bound that could be improved, cannot be improved. For the pure quadratic nonlinearity. The log T in the phase that you just mentioned, that's very important. If you couple the quadratic to cubic, that's extremely difficult. We haven't succeeded in going to infinity if you couple quadratic and cubic.
But you just showed that BTF is equal to some term that is explicit in log T over T times the coefficient that depends on them. So you would still be able to put potentially an ODE that would be in time log T, and that if you were to integrate it.
Yeah, I hear you, but this is not what happens. So we will have to look at the details. It's really a theorem that the log T over root T slowdown does happen. And maybe if we look, but again, it's not enough to have this non-dimension. You see the leading order log T over root T comes with a coefficient. So that coefficient has to be non-dimension. And then you have log T over root T.
The coefficient depends on that.
On the data. So it's checkable.
That's when it's f of t or BTF.
Let's look at the statement of the theorem. It's like this long. Okay?
Well, thank you.
So let's take a look and see what it is.